Hello, in this video we're going to be completing this table, often using trigonometric identities to help us. So no messing around, the table is now complete. And I'm going to go through in pairs and show you how to do each pair. To help me do that, I have coloured them in pairs. So we have sin x and cos x together, tan x and cot x together, sec x and cosec x together, sin squared x and cos squared x together, tan squared x and cot squared x together, and sec squared x and cosec squared x together. And you can see the same image behind me. So let's start with a pair we already know. We're aware of the circle of trigonometric differentiation, and if we want to integrate, we can go anti-clockwise around the circle. So the integral of sine is minus cos x, and the integral of cos x is sin x. I'm not going to look at them in order. I'm going to go straight down to the bottom for the integrals of sec squared x and cosec squared x. Now, we've met this table top right before, the trigonometric differentials. So if we know that the differential of tan x is sec squared x, that implies that the integral of sec squared x is tan x. And similarly, if we know the differential of cot x is minus cosec squared x, because it begins with a c, then we know that the integral of cosec squared x is minus cot x. Very closely related to that are the integrals of tan squared x and cot squared x. Now we know that tan squared x plus 1 equals sec squared x, and hence tan squared x equals sec squared x minus 1. So if we want to integrate tan squared x, that is the same as integrating sec squared x minus 1. We know that the integral of sec squared x is tan x. We know the integral of 1 is x. So the integral of tan squared x is tan x minus x plus c. And using exactly the same logic, we know that cot squared x plus 1 is cosec squared x. So cot squared x is equal to cosec squared x minus 1. We know that the integral of cosec squared x is minus cot x. So the integral of cot squared x is minus cot x minus x plus c. We will be looking at the method to integrate tan x and cot x soon, but for the time being, as it says, let's prove these results by differentiation. So I'm claiming that the integral of tan x is log sec x, so let's differentiate log sec x and show what we get. So we can apply the chain rule, so we can say that y equals log u, where u equals sec x, and then the chain rule says that dy by dx equals dy by du times du by dx. If y equals log u, then dy by du is 1 over u. If u equals sec x, then du by dx is sec x tan x. So we get sec x tan x over u, where u is sec x. The sec x's cancel and leave us with tan x. So if y equals log sec x, then dy by dx is tan x, and hence the integral of tan x is log sec x. And in the same way, if we start with y equals log sin x, y equals log u, where u is sin x, dy by dx is 1 over u times cos x, i.e. cos x over u. Since u is sin x, we get cos x over sin x, which is cot x. Now, we aren't expected to know a method to integrate sec x or cosec x, so we can just look them up in the formula book. And as you can see, as well as the integrals of sec x and cosec x, although they've written them as sec kx and cosec kx, we also have the integrals of sec squared kx and tan kx and cot kx. Having said that, we can also prove the results by differentiation like we did for tan and cot. So if y equals log of sec x plus tan x, then y equals log u, where u equals sec x plus tan x. Dy by dx is 1 over u multiplied by sec x tan x plus sec squared x. That should be in brackets really. So that gives us sec x tan x plus sec squared x over sec x plus tan x. And then if we factorise sec x on the top, we can cancel out the sec x plus tan x, and that leaves us with sec x. And again, we're just repeating ourselves here. If y equals minus ln of cosec x plus cot x, then y equals minus ln u, where u is equal to cosec x plus cot x. So dy by dx is minus 1 over u times, again in brackets, minus cosec x cot x minus cosec squared x. So all the minuses cancel out. That gives us cosec x cot x plus cosec squared x over cosec x plus cot x. Factorising out the cosec x on the top means that we can cancel out the cot x plus cosec x's, and that leaves us with cosec x as the answer. And then finally, the integrals of sin squared x and cos squared x. In order to do those, I use the double angle formula for cos. You may remember it comes in more than one form. So for integrating sin squared x, I'm going to use the version which is in terms of sin squared x. So cos 2x equals 1 minus 2 sin squared x. If we rearrange that to make sine squared x the subject, we get a half minus a half cos 2x. The integral of a half is a half x. And if we want to integrate a half cos 2x, I've written chain rule there, but it's the opposite of the chain rule, it's integration by substitution. That gives us a quarter sine 2x. So the integral of sine squared x is a half x minus a quarter sine 2x. And you can already see from the table that the difference between the integrals of sine squared and cos squared is just that sign, the minus and the plus in between the terms. So the same process for cos squared x. We use the double angle formula for cos 2x in terms of cos squared x, which is 2 cos squared x minus 1. And making cos squared x the subject, we get a half plus half cos 2x. So the only difference between that and sine squared x is the sign between the terms. So integrating them, again, we're using integration by substitution for the half cos 2x. We get an answer of a half x plus a quarter sine 2x. So in summary, as I mentioned at the beginning, they come in pairs. So for sine x and cos x, we differentiate those from first principles to get our circle for trigonometric differentiation. And if we go anti-clockwise around that circle, we get the integrals of sine and cos. For tan x and cot x, we will be learning how to integrate those by substitution, but for the time being, we differentiated their integrals to get the tan x and cot x. And for sec x and cosec x, you don't actually need to know how to integrate those, but again, we looked at differentiating their integrals, but they are in the formula book, so you don't need to learn them. For sine squared x and cos squared x, we use the double angle formulae for cos. For tan squared x and cot squared x, we use the identities. So tan squared x plus 1 is sec squared x, and cot squared x plus 1 is cosec squared x. And if we use the results at the bottom, that the integral of sec squared x is tan x and the integral of cosec squared x is minus cot x, we can integrate our tan squared x and our cot squared x. Thank you very much.